This video is going to be about solving linear equations with one variable. A linear equation is one in which you can write in the form ax plus b equals 0, where a and b are real numbers and a is never 0. However, b could be 0. So we could say that 2x equals 0 would be a linear equation where b is 0. However, you could not say that 3 equals 0 is a linear equation because there is no x anymore. So a cannot be 0, and a linear equation means that you can write it in that form. What we are concerned with is solving equations with that one variable, or solving for the values of x in which that makes the equation true. We have two examples here that we are going to be looking at. When I want to solve equations, I want to use inverse operations in order to isolate the variable. So here I'm seeing that we have 2x plus 7 equals 19. If I want to isolate the variable, I want to work with the variables that are not multiplied or divided with first, or not the variables, excuse me. I want to work with the numbers, the b number that is not associated with the x first. So I'm going to leave this alone and notice that I have this plus 7. Well, the inverse operation of adding 7 would be subtracting 7. So I can do that to both sides. That gets rid of my 7 on the left-hand side, and I know that in order for the first equation to be true, that 2x must be equal to 12. So I'm just moving that 7 over to the other side. I do that with inverse operations. And in order for that original equation right here to be true, I know that 2x must be equal to 12. If I take 12 and I add 7 to it, I would get 19. Then I work with my a value here. So the inverse operation of multiplication is division. I apply that inverse operation to both sides, and I see that x must be equal to 6. If I go back and check my work, I'd be like, okay, yeah, well, 2 times 6 does get me 12, and 12 plus 7 does get me 19. And so that's going to be my one x value that makes the equation true. When x is equal to 6, 2x plus 7 is equal to 19. Let's look at one that's a little bit more involved here. So if I notice how this is set up, I know that there's x values, there's an equal sign, and then there's going to be just constant terms. I want each one of these to look like that ax plus b on both sides, and I'm going to do that with some distribution first. So I'm going to look at my first piece here. If I distribute the 4 to both, I get 4x minus, and then 4 times 3 would give me 12. I'm then going to keep that 12 piece here. I'm going to let that be equal to 15. And then same thing, I'm going to distribute that -5 to both the x and the 6. So I'm going to say -5 times x, and then maybe plus or minus, it doesn't really matter here, but -5 times 6 gives me -30. All right, now again, I want these to look like that ax plus b on both sides so that I know that it's a linear equation. On this left-hand side, I notice that -12 and positive 12 cancel, and I get 0. So I'm just left with 4x on this left-hand side. On the right-hand side, I'm going to write my ax term first. So I have -5x. And then I'm going to combine my b terms, or my like terms that are just constants. And when I do that, I have 15 minus 30, so I get -15. I then have a couple options that I can do. I want to get my x's on the same side so that I can try to figure out what x value this would be equal to so that this equation, it has equality back up here at the original. I'm going to choose to move this x over here, again using inverse operations, adding 5x to both sides so that this side cancels. And I get 9x equals, and then my negative 15 stays on my right-hand side. I'm then going to divide both sides by 9 because the inverse operation of multiplication is division. And I do not have an integer answer like I did in the first one. I'm going to have this rational number. It's negative. And again, I could go through and I could check and make sure that that is true, that when I plug in that x value, I do get equality and the same number on both sides.